While the world's gaze is fixed on 3I Atlas, that spectral wanderer from the depths of interstellar space, a far more immediate and tangible threat is closing in on us. It's an event locked in time, a date etched into the celestial calendar by the unyielding laws of orbital mechanics. Mark it down, April 13th, 2029. On that day, an asteroid named Apophis, after the Egyptian god of chaos and darkness, will not just pass by Earth, it will intrude upon our very own backyard, soaring beneath the fleet of satellites that form the backbone of our modern world. 30,000 kilometers, that's closer than the origin point of the GPS signal guiding your drive home. The official line from space agencies is a unified, calming chorus. We are safe. But what if that reassurance is built on a foundation of incomplete data? New models, buried in the quiet corners of scientific literature, suggest this flyby is not an ending, but a beginning. The gravitational embrace of our planet could fundamentally reshape this mountain of rock, altering its surface, its spin, and its ultimate destiny in ways we are only beginning to model. This close encounter might set in motion a chain of events that culminates in a threat we are, right now, by our own complacency, creating. Stay with me, because what happens on an afternoon in 2029 could determine the safety of our planet for decades, even centuries to come. The story is unfolding in real time, and we are all witnesses. If you're as captivated by this as I am, and you want to follow every development of this story as we race towards 2029, make sure to subscribe to this channel. Leave a comment down below. Tell me where in the world you're watching from, what time it is there right now, and what you think will happen when the god of chaos comes knocking. Are we truly safe? Or are we clinging to a comfortable lie? Let's talk about what we're actually facing. While the world fixates on a distant interstellar ghost, a known entity is bearing down on us. Its name is 99942 Apophis. This chunk of rock, roughly 340 meters across, a size capable of unleashing the energy of hundreds of nuclear weapons should it ever strike, is going to pass so close to Earth that it will literally thread the needle between our atmosphere and the geostationary satellite belt. For perspective, the International Space Station orbits at about 400 kilometers. Apophis will be 75 times farther out than that, yet still absurdly, terrifyingly close for an object of its mass. This is an event unprecedented in recorded human history. You will be able to see it with your naked eye from some parts of the world. A bright, fast-moving point of light, a new star briefly blazing a trail through the constellations. People will gather, children will point, and it will trend on social media for a day. And then, the world will move on, assuming the danger has passed. But here is the question that keeps planetary scientists awake at night, the one that NASA and the European Space Agency carefully avoid in their public statements. What if that close approach doesn't just give us a spectacular show? What if it changes Apophis itself? What if Earth's gravity doesn't just give it a gravitational nudge, but actually physically reshapes it, spins it differently, triggers landslides on its surface? And what if those subtle, invisible changes set Apophis on a new trajectory, one that brings it back? The official line is math, checked and rechecked. No impact risk in 2029 or for the next century. But scratch the surface of that confidence and you find dynamicists, scientists who specialize in orbital calculations, still publishing papers, still modeling tiny accelerations, still mapping uncertainties. Why would they do that if the case was closed? Because they know something the public doesn't fully grasp. The 2029 flyby isn't the conclusion, it's the opening chapter. It's the moment when small, unaccounted for uncertainties could bloom into catastrophic ones. Our margin for error, the buffer that currently keeps us safe, could evaporate in a matter of hours. Think of it this way. All our models, our reassuring projections, are built on assumptions. We assume Apophis is a certain mass. We assume its surface reflects light in a certain way. We assume it rotates at a certain steady rate. But what happens when some of those assumptions are wrong? What happens when the rock that emerges from Earth's gravitational field isn't quite the same rock that went in? The answer is that our century-scale safety projections could become obsolete overnight. We could be looking at a completely different threat landscape, and we might not even know it for months or years. This isn't fear-mongering. This is what the cutting-edge research is quietly saying. So, while everyone watches the distant, harmless visitor, the real story is unfolding much closer to home. The god of chaos is coming, and when it arrives, we'd better hope we understand it as well as we think we do. Because if we don't, April 13th, 2029 won't be remembered as the day we dodged a bullet. It will be remembered as the day we sealed our fate and didn't even know it. Let's talk about what NASA and the European Space Agency actually said. Not the headlines, not the social media posts, but the carefully worded statements from the organisations whose job it is to monitor these things. In March of 2021, the ESA officially removed Apophis from its risk list. NASA followed suit. The key phrase everyone latched onto was that Apophis posed no risk of impact for at least the next century. The case was closed. The internet could stop freaking out. We are safe. Except that's not quite the full picture. Those statements are technically accurate based on current data and current models, but they come with invisible footnotes that nobody reads. Footnotes about confidence intervals, measurement uncertainties, and physical processes we're still characterizing. The scientists who study asteroid dynamics haven't stopped working on Apophis. If anything, their research has intensified as 2029 approaches. They're not publishing papers that scream, "We're all going to die." They're publishing papers with titles like Tidal Resurfacing Model for Apophis and Constraints on Yarkovsky Acceleration and Post-Encounter Orbital Evolution. Academic, technical, easy to ignore. But read those papers and a different story emerges. A story about forces so small they barely exist, but so consequential over long timescales that they could rewrite everything. Let me introduce you to the Yarkovsky effect. Imagine an asteroid tumbling through space. The sun heats one side. That side radiates the absorbed heat back into space as infrared light. But the asteroid is rotating, so by the time the heated surface faces away from the sun and releases its energy, the asteroid has turned slightly. The result is a tiny, tiny thrust, like a bottle rocket firing constantly in one direction. Over years and decades, this imperceptible push can shift an asteroid's orbit measurably. For Apophis, the Yarkovsky effect matters because we don't know its exact strength. We don't know the asteroid's thermal inertia, its surface roughness, or its rotation state well enough. All these factors feed into the calculation, and all carry uncertainties. Now add the 2029 flyby into the mix. When Apophis screams past Earth, our planet's gravity will squeeze it. Tidal forces will stress the asteroid's structure. If Apophis is what scientists call a rubble pile, a loosely bound collection of rocks and dust, those tidal forces could trigger landslides, shift surface material, and expose fresh rock with different thermal properties. Change the surface, and you change the Yarkovsky effect. Change the Yarkovsky effect, and you change the orbit. Change the orbit, and suddenly those century-scale safety assurances are based on outdated assumptions. The numbers are sobering. Orbital dynamicists have shown that a velocity change of just millimeters per second, sustained over years, can translate into positional differences of thousands of kilometers down the line. It's like aiming a rifle. A tiny deviation in the barrel's angle becomes a massive miss at long range. Except we're not trying to miss. We're trying to predict where the bullet will be. And we're realizing the barrel might be wobbling in ways we didn't account for. Recent modeling suggests even if just 1% of Apophis's surface experiences change during the flyby, it could be enough to alter its thermal properties measurably. 1%. That's not a catastrophic reshaping. It's a subtle modification you might not even see with a telescope, but it's enough to matter. When NASA says, "no risk for a century," what they mean is, based on our current best understanding of this object's properties, we calculate no significant probability of impact. It's a conditional, model-dependent statement. It's only as good as the data feeding it. So what happens at the 2029 flyby reveals that some of our assumptions were wrong. We start over. We recalculate. And we hope we have enough time to do something about what we find. Research team led by Dr. Kim published a paper that sent quiet shockwaves through the planetary defense community. The title was technical and forgettable. The implications were anything but. They had built a detailed model of what would happen to Apophis physically during the 2029 encounter, not just its orbital path. They simulated what Earth's tidal forces would actually do to the rock as it passed through our gravitational field. Their conclusion was startling. They found that roughly 1% of Apophis's surface might experience resurfacing during the flyby. Material movement, grain flow, essentially landslides happening in slow motion, as Earth's gravity kneaded the asteroid like dough. 1% sounds trivial, easy to dismiss, but context is everything. That 1% represents potentially millions of tons of material shifting position. Fresh rock exposed, dust redistributed, the asteroid's reflectivity altered in localized patches. And as we just discussed, change the surface and you change the Yarkovsky effect. Change the Yarkovsky effect and you change everything downstream. The Kim paper opened the door to a cascade of new questions. If tidal forces can trigger surface movement, what else might they trigger? Could they change the asteroid's spin rate? Could they nudge it into a tumbling state? Let's walk through the chain of causation, because this is where tiny changes become huge consequences. Start with the flyby. Earth's gravity squeezes Apophis. Surface material shifts. A patch of darker, less reflective rock gets exposed. That patch absorbs more sunlight and radiates more heat. The Yarkovsky effect in that region strengthens slightly. Over years, that extra thrust accumulates. The asteroid's orbit bends by kilometers, then tens of kilometers, then hundreds. Now, project forward to 2036, when Apophis makes another relatively close pass. Except this time, because its orbit was nudged by that altered Yarkovsky effect, it's not quite where the old models predicted. Maybe it's a few hundred kilometers off. At the scale of the solar system, that's nothing. At the scale of hitting or missing a planet, that's everything. The model showed something else troubling. If Apophis does experience significant rotation changes, our ability to predict its future Yarkovsky acceleration degrades dramatically. A simply rotating object is predictable. A tumbling object is chaotic. The thermal thrust vector precesses wildly. The orbit becomes harder to calculate. The uncertainty bands widen. Predicting an asteroid's position in 50 or 100 years requires accounting for every tiny force acting on it over that entire period. Miss a force, or miscalculate its magnitude, and your prediction will be wrong. The 2029 flyby is a giant reset button on our understanding of Apophis. Everything we think we know about its properties could change in a matter of hours. We will need to remeasure everything afterward, rebuild our models, recalculate the risk. That takes time, and during that time, Apophis will be drifting along an orbit we no longer fully understand. Other researchers have picked up this thread. There are papers now exploring what if the rotation change is more dramatic? What if the surface change is concentrated in a specific region? What if the asteroid's internal structure is weaker than we thought? Each scenario opens new branches in the probability tree. We won't know which branch is reality until after the flyby happens. Think about it like predicting the path of a train. You know its speed and the track layout. You can calculate its arrival times. Now imagine someone tells you that at one station, workers might adjust the track slightly. Not derail it, just tweak the alignment by a few degrees. Suddenly, your predictions for stations farther down the line become less certain. You have to wait for the train to pass that station, see what actually happened, and then recalculate. Apophis is the train. The 2029 flyby is the station, and we're all waiting to see if the tracks get adjusted. Is a scenario that keeps appearing in the technical literature, one that sounds too much like a disaster movie, so nobody discusses it in plain language. But it's grounded in real physics and real observations. What if Apophis doesn't just change slightly during the flyby? What if something breaks? Not a Hollywood shattering, but in the more subtle, insidious sense of an object that's barely holding itself together, losing its tenuous structural integrity. Let me explain what we mean by a rubble pile. Many asteroids aren't solid chunks of rock. They're more like beanbags, collections of boulders, pebbles, and dust, all clumped together by their own weak mutual gravity, and maybe some cohesion from fine dust acting like glue. They are fundamentally fragile. Laboratory experiments show how little force it takes to initiate landslides in this kind of material. Now, subject that structure to tidal stress. The near side of Apophis will feel Earth's gravity pulling harder than the far side. This creates a stretching force across its diameter. For a solid object, no problem. For a rubble pile, that's a different story. Imagine a bag filled with marbles. Pull gently on opposite sides and nothing happens. Pull harder and the marbles start shifting. Pull hard enough and they redistribute, changing the bag's shape. The 2023 Kim tidal resurfacing model suggested this kind of surface movement is plausible. But what if it goes further? What if subsurface structures shift? What if the asteroid's shape deforms measurably? What if, in a worst-case scenario, a chunk actually separates? This isn't wild speculation. We have precedent. Binary asteroids exist, pairs of rocks likely formed when a parent body was stressed enough to split. If Apophis loses mass during the flyby, everything changes. Your mass estimates are wrong, so your gravity calculations are wrong. Your rotation modelling is wrong. Your Yarkovsky predictions are wrong. You now have two objects to track instead of one, and the smaller fragment might be on a completely different trajectory. The really troubling part is that a small fragment separating might not be immediately obvious. If a boulder gently drifts away at a few centimeters per second, it could take weeks or months of observation to confirm it happened. During that time, we're tracking what we think is a single object, building models based on a false assumption. If that fragment is on a different orbit, it could end up hitting Earth, even if the main body misses. You've just turned a single probability calculation into a multiple body problem. The analogy is a snowball rolling downhill. A compact snowball has a predictable path, but if that snowball starts shedding chunks or deforming as it rolls, the prediction becomes much harder. Small changes early in the roll create wildly different outcomes at the bottom. Apophis is the snowball. The 2029 flyby is the top of the hill, and we don't know yet whether it will reach the bottom intact. Let me tell you a story about how close we came to a very different timeline. In December 2004, astronomers discovered Apophis. Preliminary orbit calculations were alarming. The initial probability assessment for an impact in 2029 was roughly 1 in 40, or 2.7%. In asteroid risk terms, that is absolutely terrifying. The reason was large uncertainties in the early data. When you propagated those uncertainties forward, a concerning fraction of the probability distribution intersected Earth. More observations came in, the orbit was refined, the probability dropped. By 2005, the 2029 impact was ruled out. But something else emerged from that analysis. A keyhole scenario for 2036. Here's how keyholes work. When an asteroid passes close to Earth, our gravity bends its trajectory. How much it bends depends on exactly where it passes. Most trajectories result in safe deflections, but there exist narrow regions in space, keyholes, where the deflection is just right to set up a future collision. Think of it as gravitational pinball. The asteroid is the ball, Earth is a bumper. Hit the bumper at the wrong angle, and the ball bounces straight toward the next bumper, which happens to be Earth again years later. For Apophis, the 2036 keyhole was a region roughly 600 meters wide that it would have had to pass through in 2029 to hit us in 2036. 600 meters sounds large, but against a close approach distance of 30,000 kilometers, it's a needle in a haystack. As observations continued, that specific keyhole was ruled out. By 2021, NASA and ESA officially declared Apophis posed no risk for at least a century. Case closed? not quite. Because while that specific keyhole is gone, the gravitational landscape is full of them. The 2029 flyby will deflect Apophis through a region where other potential keyholes exist for encounters in the 2040s, 2050s, and beyond. We haven't mapped them all. We can't, not with current uncertainties. The geometry is unforgiving. Before 2029, Apophis orbits with a period of about 0.9 years. After the flyby, Earth's gravity will kick it into a larger orbit with a period of about 1.2 years. It transitions into a different class of asteroid. This sounds like good news. It's being pushed farther out on average. But what matters isn't the average distance, it's the points where its orbit intersects Earth's. And the flyby could position Apophis such that future close approaches become more likely, not less, especially if it gets locked into a gravitational resonance with Earth, a stable, repeating orbital relationship. If Apophis ends up in resonance, we'll be seeing it repeatedly every few years. Each encounter is another chance for gravitational perturbations, another roll of the dice. This is why the flyby is a pivot point. It's not just an event, it's a branching. Before the flyby, we're on one trajectory branch. After, we're on another. And which branch we end up on determines the risk landscape for our grandchildren. The most likely scenario is that Apophis flies by safely and does not return as a threat. The smart money is on everything being fine. But science isn't about the most likely scenario, it's about understanding the full range of possibilities. And the tail scenarios, the low probability but high consequence outcomes, are still on the table. They're still being researched. They're still keeping some scientists up at night. There's a force acting on Apophis right now that's weaker than a mosquito landing on your arm. A force so subtle that detecting it requires years of patient observation. A force that over decades could mean the difference between a safe passage and a collision. It's the Yarkovsky effect, and it's one of the most important things you've never heard of. The concept is simple. Asteroids absorb sunlight, heat up, and radiate that energy as infrared light. But because they're rotating, the hottest part, the afternoon side, radiates more heat when it's facing away from the sun. Those escaping photons carry momentum, pushing against the asteroid and creating a tiny thrust. For a rotating body, this thrust isn't symmetric. It creates a net force that either speeds the asteroid up or slows it down in its orbit. The numbers are absurd. Accelerations measured in fractions of a nanometer per second squared. A force 10 billion times weaker than Earth's gravity. You could replicate it by breathing gently on a boulder. But apply that breath for 20 years and you've moved the boulder kilometers. Apply it for a century and you've moved it tens of thousands of kilometers. For Apophis, the Yarkovsky effect matters because we don't know its magnitude precisely. We have constraints, but the variation comes from uncertainties in parameters we can't directly observe from Earth. Thermal inertia, surface roughness, composition. Now here's where the 2029 flyby becomes critical. Remember those tidal forces that might trigger surface changes? If the flyby alters Apophis's surface properties, the Yarkovsky effect changes. Fresh rock might have different thermal inertia. Dust redistribution might change its reflectivity. And then there's the rotation complication. What if Apophis is tumbling, rotating chaotically around multiple axes? Tumbling asteroids have been observed. It makes predicting their thermal behavior exponentially harder because the sun-heated surface is no longer predictable. The Yarkovsky thrust vector wobbles chaotically. If the 2029 flyby nudges Apophis into a tumbling state, our ability to predict its future trajectory degrades significantly. The neat orbital projections that extend a century into the future suddenly have much wider error bars. This is where measurement error propagation becomes a nightmare. In orbital dynamics, small errors in initial conditions grow over time. If your measurement of Apophis's current position is off by 1 kilometer, your prediction of where it will be in 5 years might be off by thousands of kilometers. Now add an uncertain Yarkovsky acceleration on top of that. The uncertainties compound. By the time you're projecting decades ahead, the possible positions form a cloud rather than a point. That cloud is what risk assessors work with. They calculate the probability that any part of that cloud intersects Earth at some future date. Right now, for Apophis, that probability is tiny. But if the cloud grows after the flyby, those probabilities increase. We are trying to predict not just one collision, but a series of potential encounters stretching decades into the future. And we're realizing that the gentle pressure of sunlight might be the one variable we can't quite pin down. When you picture an asteroid, you imagine something solid, a chunk of iron or stone. For many, that picture is wrong. The term of art is rubble pile. It sounds comical, but it describes a real and terrifying physical configuration. A rubble pile asteroid is a gravitationally bound aggregate, a collection of smaller rocks from house-sized boulders down to fine dust, held together by mutual gravity and weak cohesion. No structural strength, just gravity and friction. This matters because rubble piles respond to stress differently. Apply force to a monolithic asteroid, and it withstands it or fractures. Apply the same force to a rubble pile, and you get deformation, grain flow, internal reorganization. The 2023 Kim paper on tidal resurfacing took this seriously. They modeled Apophis as a rubble pile with various assumed internal properties, porosity, cohesion, angle of repose, and subjected it to the tidal stress of the 2029 flyby. The results showed that even with conservative assumptions, surface material movement was plausible. Slopes would fail, material would slump, the surface would rearrange itself. 1% of the surface is thousands of square meters. Picture a hillside the size of several football fields experiencing a landslide in slow motion. Now, scale up the what if. What if Apophis's internal structure is weaker than the models assumed? What if the porosity is higher, meaning more empty space and less integrity? Laboratory experiments on meteorite samples show how fragile these materials can be. They have almost no tensile strength. If Apophis is similar, the tidal forces aren't a theoretical concern. They're a potential trigger for major structural change. Think of a beanbag chair. Squeeze it and it adapts. The beans inside flow to accommodate the force. Now imagine that beanbag is 340 meters across and flying through an intense gravitational field. The beans are going to move. And moving beans means moving mass. Changing the mass distribution changes the moment of inertia, which affects how the asteroid spins. Spin changes feed into thermal modeling, which feeds into Yarkovsky predictions. Everything is connected. There's a darker possibility: rotational breakup. If the flyby spins Apophis up, increasing its rotation rate beyond a critical threshold, centrifugal forces could overcome gravity. The asteroid could start shedding material from its equator, or even split. We've observed this happen to other asteroids. The calculations suggest the tidal torque during Apophis's flyby is too weak for this. But those calculations assume we know its current rotation state and internal structure accurately. Do we? The answer is, we think so, but there's uncertainty. And in that uncertainty lives risk. Apophis is a bridge. The 2029 flyby is the load test, and we're not entirely sure what the bridge is made of. Let's pull the camera back for a moment. Our ability to track Apophis, to monitor its orbit with the precision needed for planetary defense, depends on a fragile technological ecosystem. Ground-based radar systems, optical telescopes, spacecraft, and the satellites that handle our communications and data. All of it is vulnerable. Consider space weather. A massive solar flare and coronal mass ejection, like the one that occurred in November 2025, can ionize our atmosphere, disrupt radio communications, degrade GPS signals, and even damage power grids. Now imagine a scenario. It's April 13th, 2029. Apophis is making its close approach. Every telescope and radar dish on Earth is pointed at it, trying to measure its post-flyby trajectory with maximum precision. And on that same day, the Sun launches a major coronal mass ejection directly at Earth. Suddenly, half your observational assets are degraded or offline. Radar tracking is unreliable. Satellite communications are intermittent. You're trying to make the most critical measurements in planetary defense history, while your instruments are being scrambled by forces completely beyond your control. This is about systemic risk. Individual threats might be manageable. Apophis is being tracked, solar storms are monitored. But when multiple stresses hit simultaneously, systems can fail in unexpected ways. There's another layer, the orbital environment itself. When Apophis passes inside the geostationary belt, it will have its own tiny gravitational field. The calculations say it's too small and fast to perturb satellite orbits meaningfully. But has that been calculated for every single satellite in that crowded highway? A distracted satellite operations community, dealing with the global event of the flyby, while also managing degraded communications from a solar storm, could make an operational error. A collision in geostationary orbit creates debris that persists indefinitely, potentially triggering a cascade, a scenario known as Kessler syndrome. Apophis won't cause it directly, but it could be the stressor that exposes the fragility of the system our planetary defense relies upon. This isn't hypothetical disaster mongering. It's a reminder that our safety doesn't just depend on understanding the rock, it depends on maintaining the complex, vulnerable infrastructure that allows us to see it. If you want to know what we actually need to learn about Apophis, focus on the data gaps, the parameters that, if measured precisely, would tell us whether the 2029 flyby is genuinely safe or just probably safe. First and most important, mass. We can't weigh it directly. Without a moon to observe, we need a spacecraft to fly close and measure the gravitational perturbation. Mass uncertainty translates directly into uncertainty about how much Earth's gravity will bend its trajectory in 2029. Second, rotation state. Is it spinning simply or tumbling? This is critical for thermal modelling and the Yarkovsky effect. Current light curve data suggests simple rotation, but it can be ambiguous. We need spacecraft-level observation. Third, shape and topography. Radar gives us a coarse model, but we need high-resolution maps to identify steep slopes and potential landslide sites before the flyby. Fourth, referral inertia. How quickly does the surface heat and cool? This is the key to the Yarkovsky effect. Our current estimates have error bars of a factor of 2 or 3. Fifth, surface composition and reflectivity. What is it made of? If the flyby exposes fresh material with different properties, the thermal balance changes. Sixth, regolith properties. Is there a thick layer of loose dust, or is it bedrock? The OSIRIS-REx mission to asteroid Bennu found a surface so fluffy the spacecraft sank in. If Apophis is similar, tidal forces will cause dramatic reshaping. Seventh, any ongoing mass loss. Is it actively shedding dust? Current observations show no evidence, but weak activity could be missed. These 7 parameters are the keys. Measure them before the flyby, and we have a baseline. Measure them after, and we see what changed. The difference tells us if our models are right. This is why the missions are so vital. OSIRIS-APEX, the redirected spacecraft, will arrive at Apophis about a month after the flyby to document the aftermath. The proposed Ramses mission by the European and Japanese space agencies would arrive before the flyby, giving us the complete before, during, after picture. These missions aren't just scientific curiosities, they are risk mitigation. Every parameter they constrain, every uncertainty they reduce, shrinks the probability cloud of Apophis's future. It gives us confidence, or it tells us we're in more trouble than we thought. The clock is ticking. We have 3 years to prepare, to get these missions approved and launched, to ready our ground-based campaigns. The measurements we make in this window will determine how we respond to whatever the flyby reveals. There's a fascinating dynamic in how space agencies communicate about asteroid risk. They have a scientific obligation to be accurate, but also a public relations imperative to avoid panic. In March 2021, when ESA and NASA removed Apophis from their risk lists, the messaging was clear and reassuring. No risk. The scientific papers published at the same time tell a more nuanced story. They include caveats, discussions of uncertainties, acknowledgements that future observations might change the assessment. This hedging is standard in science, but doesn't make it into press releases. Why the discrepancy? Institutions operate under different incentives. An agency must balance scientific accuracy with public trust. Say too much about uncertainties, and you risk panic and cries of incompetence. There's also the mission planning angle. ESA is seeking approval for the Ramses mission. Its scientific case rests on the flyby being a unique opportunity. But if the agency simultaneously talks about significant risk, the mission becomes politically fraught. Is it science or planetary defense? The optics get complicated. Similarly, NASA redirected OSIRIS-APEX to Apophis because we need the measurements. With the unspoken subtext, we need to know if our models were wrong. This isn't a conspiracy, it's how institutional communication works. When an agency says, no significant risk, it means no risk above our threshold for public notification given current data. Risks below that threshold are still researched, but not publicly highlighted. Look at the publication record. Papers on Apophis haven't stopped. Researchers are still modelling, still exploring. The work continues because the case is never fully closed in science. There's always more precision to be gained. But that ongoing, careful work doesn't make headlines. The headlines were in 2021. Asteroid Apophis won't hit us. The story since then has been one of quiet, diligent refinement. For someone trying to understand the real situation, the strategy is to read the primary scientific literature, not the press releases. Look for phrases like requires further observation or uncertainties remain. That's where the real story lives. And that story shows that while agencies are publicly confident, researchers are still actively working to nail down the parameters that determine our long-term safety. Characterization of asteroid science is a history of surprises. When the Galileo spacecraft flew by asteroid Gaspra in 1991, scientists expected a cratered, inert rock. They found grooves and fracture patterns, evidence of a complex geological history. When the near Shoemaker spacecraft orbited Eros, it found a surface covered in house-sized boulders sitting in fine dust, a dichotomy we're still trying to explain. When Hayabusa reached Itokawa, it discovered a rubble pile, a collection of fragments that had reaccumulated. When OSIRIS-REx touched down on Bennu, it expected a firm surface. Instead, the sampling arms sank into a material with the consistency of a ball pit. Every close encounter with an asteroid has revealed something unexpected. Every mission has forced us to revise our assumptions. Why should Apophis be any different? The James Webb Space Telescope provides a perfect analogy. Since it began operations, JWST has consistently delivered surprises. Galaxies that are too old and too massive, complex chemistry emerging too early in the universe. A more powerful instrument doesn't just confirm what we know, it reveals what we didn't know to look for. OSIRIS-APEX and Ramses are our JWST for Apophis. They will see details we can't see from Earth. They will measure things we can't measure from here. And they will almost certainly reveal surprises. The question is whether those surprises will be benign curiosities or game-changing discoveries that force us to recalculate risk. We are in the position of astronomers before JWST launched, confident in our models, but aware that surprises are not just possible, they are likely. The difference is that JWST's surprises change textbooks. Apophis's surprises could change survival odds. So, let's bring this all together. Let's talk about what actually matters as we approach April 13th, 2029. Apophis, the god of chaos, is coming. Not as an immediate threat, but as a test. A test of our understanding, our capabilities, and our preparedness. The asteroid will pass breathtakingly close, an event that will be visible, sensational, and then largely forgotten by the public. But for those who know, the real work begins the moment it passes. The flyby is the moment when subtle forces could reshape the long-term risk landscape. The Yarkovsky effect, tidal reshaping, rotation changes, the remote possibility of fragmentation, all will be tested. The measurements we make in the years before, and especially in the days and months after, are everything. They will collapse the uncertainties that currently cloud our view of the future. The missions, Osiris Apex and, we must hope, Ramses, are our eyes and hands. They are not optional. They are fundamental to planetary defense. The policy steps are clear. Full funding for these missions, open data sharing among all nations, and serious contingency planning for deflection missions. Not because we expect to need them, but because if the post-flyby data demands it, we must be ready to act. This is the unglamorous reality of planetary defense. It's not about last-minute heroics. It's about the patient, careful, incremental work of observation, modelling, and refinement, year after year, building the understanding that lets us say, with confidence, that we know what this rock will do, or finding out that we don't, and adapting accordingly. The countdown to April 13th, 2029 has begun. 3 years and counting. We need to use this time wisely. We need to watch, to measure, to prepare. Not with panic, but with purpose. Because the ability to look up, to track the sky, to calculate orbits, and to ask, what if? That is what makes us different. That is what gives us a chance against threats that our ancestors could only attribute to angry gods. The god of chaos approaches, and when it arrives, we will know if we were prepared. I hope we are. I think we are. But I'm watching the data, just in case. Because hope is not a strategy. Knowledge is. Preparation is. Vigilance is. And that vigil must continue until we know with certainty where Apophis will be, not just in 2029, but in every future encounter for as long as it matters. That's the work. That's the commitment. That is what it means to take our place in a solar system that is still very much alive. There is a ghost in the data, a whisper of uncertainty that no amount of current observation can fully silence. It's the ghost of unmeasured parameters, of physical properties we can only infer from a distance. Our entire edifice of prediction for Apophis rests on a foundation of estimates. We have estimated its mass based on its size and an assumed density, but we have not weighed it. We have estimated its internal structure by comparing it to other asteroids, but we have not peered inside. We have mapped its gross shape with radar, but we do not know where the fractures lie, where the overhangs loom, where the loose regolith is piled deep. This ghost manifests in the wide error bars of our long-term projections. It is the reason why, despite all our assurances, the probability cloud of future positions never shrinks to a single, unambiguous point. It is the reason the keyholes for the 2060s and 2080s remain faintly shaded on the dynamicists' maps, not as imminent threats, but as regions that cannot yet be definitively ruled out. This ghost is what separates probably safe from definitively safe. We are navigating by a map that is 99% complete, but the missing 1% could be the location of a cliff. The 2029 flyby is our one chance to exorcise this ghost, to replace estimation with measurement, to swap inference for direct observation. The spacecraft missions are not merely scientific instruments. They are instruments of exorcism, designed to banish the spectre of ignorance that has haunted our models for 2 decades. When Osiris Apex and, if we are wise, Ramses point their instruments at Apophis, they will be illuminating the shadows where our uncertainties hide. They are not just going to an asteroid, they are going on a ghost hunt. And what they find will determine whether we can finally rest easy, or if we must prepare for a longer, more complex vigil. In the sterile language of orbital dynamics and thermal models, it is easy to forget the human chain that makes this knowledge possible. It stretches from the engineer who designed the CCD sensor on a telescope in Chile, to the graduate student who painstakingly analyzes the pixel-by-pixel brightness of a star field to pinpoint Apophis's position, to the radar technician who spends a cold night aiming a massive dish at a point of reflected light, to the programmer who writes the algorithms that filter out the noise of the universe to find the signal of a drifting rock. Planetary defense is not an abstract concept run by machines. It is a profoundly human endeavor, fueled by curiosity, diligence, and a deep-seated desire to protect our shared home. This human chain has weaknesses. It depends on funding cycles that can be capricious. It relies on international cooperation that can be strained by terrestrial politics. It requires public support that can be fickle, swinging from apathy to alarm based on a headline. The greatest threat to our planetary defense may not be an asteroid, but our own human nature, our tendency to prioritize the immediate over the long term, to slash budgets for programs that protect us from low-probability events, to ignore a problem until it is at our doorstep. The story of Apophis is a test of this human element as much as it is a test of our physics models. Can we, as a global society, maintain the focus, provide the resources, and foster the cooperation required to see this through? Can we support the quiet, unglamorous work of observation and calculation that must continue for decades, long after the spectacle of the 2029 flyby has faded from memory? The asteroid doesn't care about our budgets or our political squabbles. It follows the laws of physics, indifferent to the affairs of the tiny beings on the blue marble it swings past. Our job is to be less indifferent than the rock. Our job is to marshal our collective human will, intelligence, and resources to ensure that when the universe throws a stone, we are not just a target, but a species that saw it coming and had the wisdom to get out of the way. So where does this leave us? On a precipice, but not of doom, a precipice of knowledge. April 13th, 2029 is not a finish line, it is a starting gun. It marks the beginning of the most critical phase in the history of Apophis, and in some ways, of modern planetary defense. The close approach will be over in hours, but the analysis will take years. The data collected in the wake of the flyby will keep scientists busy for a generation. We will learn if our rubble pile models were correct. We will learn if the Yarkovsky effect behaves as predicted on a freshly resurfaced asteroid. We will learn if we truly understand the mechanics of chaos. And based on what we learn, we will make a choice. If the data shows the asteroid settling into a benign orbit, clear of keyholes for centuries, we will stand down, our models validated, our confidence earned. But if the data shows the asteroid on a new path, one that threads a gravitational keyhole and puts it on a return course for a future decade, then a new chapter begins. The chapter of deflection. The technology exists: kinetic impactors, gravity tractors, ion beam shepherds. They are no longer science fiction, but they require time, money, and international consensus to deploy. The long watch will then become a countdown to a rendezvous, a mission to nudge the god of chaos ever so slightly onto a safer path. This is the ultimate goal, not just to predict, but to protect. The vigil we keep now, with our telescopes and our probes, is what gives us the time and the option to act later. The story of Apophis is the story of our evolution from a species that was struck by asteroids to a species that studies them, tracks them, and one day will deflect them. It is the story of replacing fatalism with foresight. The clock is ticking down to 2029, but for those who understand, the real clock, the long clock of planetary defense, never stops. It ticks with every observation, with every refined calculation, with every new discovery. We are the first generation to have this responsibility, to have this capability. The god of chaos is coming, and we are watching.